Yeah, so I really appreciate the opportunity to be here. My name is Jake Vanderplas. I work across the street over in the eScience Institute on campus. And essentially what we do in eScience is we're trying to provide a little bit of a glue between all different departments on campus. People in statistics and computer science that are working on methods, and then people in astronomy, oceanography, atmospheric science who are working on kind of domain science using those methods. My background is in astronomy, so I'm going to talk a little bit about statistics, data mining, and machine learning in astronomy. And in particular, one thing that's kind of interesting about these things in astronomy is they don't really work that well, at least straight out of the box. So I want to tell you a little bit about some of the challenges of applying some of these methods in astronomy, and kind of the ways that we've gone in the community that we've adapted these methods so that they actually do work. I also want to apologize. This is my first morning here because I was in the Willamette Valley as well for the last 2 days. My mom lives in Corvallis, Oregon, in the Path of Totality, and I think I put it on her calendar in like 2011 that I was coming this weekend. So it was an amazing event down there, and it's good to be back here. So anyway, in astronomy, you have a number of challenges that aren't present in the fields that tend to develop statistics and data mining machine learning techniques. One is that the data are often quite noisy, and we have really good models of that noise from, for example, Poisson statistics on detector counts when you're looking at images of distant objects. We often have very biased sets of pre-labeled objects. You know, people tend to spend a lot of time observing the brightest objects in the sky, and it's harder to get information about the faintest objects in the sky. So our labeled objects are the brightest ones, and that means you can't just run a machine learning algorithm and get those labels for the faint objects often. And the other thing is that data are fundamentally image-based, and there's not a lot of platforms out there that do image analysis at scale out of the box. And so I'm going to talk about a few case studies of these sorts of problems and what we've done in the community to get around that. So in general, in astronomy, we've been able to progress in these computational methods by adapting and extending standard things that are out there from other fields. So I want to go through 3 case studies, one in statistics, one in data mining, one in machine learning. And the first one I want to talk about is in statistics, this idea of generalizing the Lom-Scargill periodigram. This is something that I worked on a couple years ago that was kind of an interesting study. And the idea is that as we astronomers look up in the sky, one thing that's fundamental in a lot of different areas is detecting periodicity in objects. Periodic variation. It might be something like a planet going around a star and eclipsing it and creating a dip in the brightness. We want to be able to detect that. Or it might be something like detecting periodic variable stars that can be used to map the structure of the galaxy, because we can use them to get distances. And in either case, what's required is to be able to look at these noisy fluctuations of light coming from the stars in the sky and recognize these periodic signals. So data might look something like this. You know, you have over the course of, what is this? This is about 6 months of data. 6 months of simulated data. You have this star that's getting brighter and fainter. And if you actually fold the data over this period of 0.6 days, you see that there's a coherent variation across those 6 months. But this is relatively difficult to do, right? To figure out the exact fold that works for this 6 months of data. So one method that's been common in astronomy for the past maybe 3 decades or more is this Lom-Scargill periodogram. And effectively what that does is it assumes a sinusoidal model to the data and tries to fit a sinusoid at each candidate period, and then constructs a periodogram that looks a lot like a Fourier periodogram but is slightly modified. And wherever the peak is right there in this kind of inverse chi-squared space tells you what the best period is, right? So this has been used a lot for years, but the problem is that it doesn't really work for heterogeneous data. And the modern surveys that we have are creating these data in multiple band passes. You know, we're observing in red and green and blue and ultraviolet and infrared. And a single Lom-Scargill periodogram is not going to work for that. If you look at if you look at multiband data like this, you can have kind of two approaches maybe based on the old periodogram. You can pretend it's all from one band and try to fit one sinusoid to everything. And that doesn't work very well because this is not a very good model for this data. Another thing you can do is you can fit a single Lomscargel periodogram in each individual band and then combine the results into one periodogram like this. And you can see either of these cases work pretty well if you have really densely sampled data, where we get a periodogram with this 0.6-day period readily visible. But if you start having sparser data, if you have maybe one observation per band per night, the periodograms don't really work out. So the question is, how do we adapt this method that's tried and true, that works in other situations, and make it work for the kind of data we're producing today in astronomy? And what we ended up doing is we basically extended this model here, and this looks like a bunch. This looks pretty complicated, but it's relatively simple if you look. If we take a look at the pieces, first we defined a base component that's kind of like a Fourier series that fits sort of the general overall variation and everything. The second component here is a band component that looks at the deviation of each individual band from that central model. And if you put them together, you get a model that models everything pretty well. And it ends up being a very complicated model, so you have to regularize it. And once we put in the regularization, we get a single periodogram that, for this sort of sparse data, is able to very accurately pull out this 0.6-day period. See, these are the individual periodograms for each band of data, the standard Lomscargel computed on each, and this is the full periodogram using this multi-band method. So basically, this is just an example of how we can take standard statistical methods and sort of open the black box and figure out what's going on inside these methods and extend them for the specific types of data that we see in astronomy. So another one, let's look at data mining here. So one case study I want to look at here is a database for images. So this is a problem that I've been working on in collaboration with some folks at the computer science department here at UW. And what we wanted to do is take a look at some of the types of data that are coming out in future surveys, like the Large Synoptic Survey Telescope. We're going to see tens of terabytes of images every night. And we need to, as a community, figure out how to, number one, make sense of those images and extract science from them. But number two, maybe the more challenging thing, is how to make those images available to the entire community, the raw images themselves, so that other people can do their own analysis. You know, it's easy enough to have a big stack of servers running your own analysis pipeline and feed people kind of processed results. But giving people access to those pixels is difficult. And that's because there's not really any database out there that's designed for holding large amounts of images and doing queries over images. So we did this paper just recently. Actually, it's being presented this month at the Very Large Database Conference. It's a comparative evaluation of big data systems and scientific image analysis. And essentially what we did is we got some astronomers, we got some neuroscientists, and had them put together a pipeline of image analysis that is typical for their field. And then we had our computer science colleagues, grad students, postdocs, and faculty, try to use existing database systems and solve those problems as fast as they could. It was a pretty fun exercise. And essentially, the challenge is that typical databases that are developed for things like, Walmart transaction records are tabular data, right? And they can do tabular data very well. But typical astronomy data is arrays of pixels, and we want to do things like co-addition of those pixels. We want to do filtering. We want to do point spread function matching and things like this. So we took a look at these 5 systems to kind of get a representation of what's available out there. And I'll go through them really quickly. One is SciDB, which you may have heard of because that was developed sort of in the context of science with the goal of being used in LSST and similar projects. And this is a database architecture purpose-built for multidimensional arrays. So we were hoping that this would be a really good use case for images, because images can be turned into these can be viewed as these multi-dimensional arrays stacked on top of each other. Spark, you may have heard of. This is an in-memory big data system, and it has a nice Python interface. It's very widely adopted. There's things like Spark ML and various libraries that are built on top of that to do more specialized things. Myria is our in-house database system developed by the database group at UW. It's a shared nothing database management system. Dask is an interesting one. It's not really a database system, but if you're in the Python world, you might have seen it. It's essentially a framework in order to parallelize Python code that you've written from the ground up. And then finally, TensorFlow. This one's a little bit of an odd duck to include here because it's not really a database system. It's not really designed for the types of problems that we're doing, but you know, it's something that's getting a lot of buzz lately, and you can map some of these problems onto it. So we took a look at all of those, and just the quick executive summary is we found that none of them really has sufficient primitive operations to do the types of image processing that we need to do in astronomy and in neuroscience. So everything that we had to do, the core chunks of the algorithms in all these systems needed to be basically user-defined functions that we put in. So user-defined function support, these first four have good support for Python user-defined functions. So that means we could take our existing pipelines and basically parallelize them on these systems. TensorFlow was a little bit harder in that case for several reasons. Data formats, you know, in astronomy, or in science, we tend to use these very not proprietary, these very specific data formats. Like in astronomy, we tend to use the FITS, the Flexible Image Transport System. Or in neuroscience, there's this other data format that's been developed and used over the last 10 years. And we found that only a few of these systems were able to handle natively these data formats, and other ones had to basically do a lot of translation of data, which slowed things down along the way. None of these systems were able to automatically tune. Every single one of them needed some degree of like specific expertise, someone who was familiar with the system to go in and say, this is what we need to do to make this work quickly on this data. And streamline installation, SciDB is I don't know if any of you have tried to install that before. It's a day-long headache if you're lucky. And the rest of them are pretty good. And then the user community we found was essential because when you run into problems, when you get an indecipherable stack trace when you're trying to run your things, you want to be able to type that into Google and find a Stack Overflow answer that tells you what to do, right? So looking at this big summary here, you can see that really none of these existing systems is well suited to the types of scientific image analysis that we want to do. In astronomy and in neuroscience. And the really exciting thing about this is now that we have, I should mention, we have a lot of graphs and like quantitative stuff in this paper right here. If you're interested in looking at the details of all of this, I just wanted to give the quick 5-minute overview. But the exciting thing here is there's really room for research in the software tools and in the hardware tools as well. And we have people now in the database group at UW who are excited about working in this direction. They have a clear view of the types of problems we have in science and the types of challenges there are with existing systems. And we have a whole group of people that are starting to work on databases for scientific images. And so in the next couple of years, I anticipate that this will be a really interesting area to follow. So that's the data mining case study, and as you can see, like I said, it doesn't really work in astronomy, but we're getting there. The last one is this machine learning case study, and I want to highlight a paper, a study that I had nothing to do with. These are colleagues at NYU who have worked on this, but this model called the Cannon is something that I've been really impressed with because what it does, it's from Melissa Ness and David Hogg and some others at NYU. But what it does is kind of take a brand new look at machine learning to address some of the challenges, the specific challenges we have in astronomy. So their goal here is they want to be able to look at spectra that look like this. You have several thousand observations in each wavelength bin. You're looking at a distant star or distant galaxy. In this case, they're stars. And from these spectra, you want to be able to derive interesting scientific quantities. For example, the temperature of the star, the surface gravity, the metal content of the star, and things like this. And so you might think, if you took a statistics and machine learning graduate class, you might think, aha, I know how to do this, right? I train the data, and I fit a support vector machine or something like that, and I predict the results, and then we write our paper, and we become famous, right? And so the textbook machine learning approach is this. You have training data in some parameter space. You make a model, which in the simplest case of classification is just a line separating one clump from another. You can do much more complicated things, but this is effectively what machine learning is, drawing a line and some points. And then you have some new data, and you say, aha, my line tells me exactly what those are, and I can label them, and then it all works, right? So this is if you take a machine learning class, this is what you learn. This is how you do machine learning. But if you come to astronomy and try to apply this, you immediately run into problems. Your data looks more like this, right? We have very noisy, faint data. And if you dig into the literature, not many people are thinking about how to fit a support vector machine to data that has measurement errors. It's just something that doesn't come up in predicting ad clicks on Amazon. But it comes up in astronomy, right? So we need to think about other things. The other problem here is that, as I mentioned before, often our training data is not statistically similar to the unknown data. So you have unknown data that's sitting out here somewhere. And if you just draw a line somewhere in here, or you try to fit a model, extrapolating that model out to data that's far fainter than you've seen in your training set is going to cause problems. So the interesting insight that this Cannon paper had is that basically it's very hard to take observed data with noise and fit a typical machine learning model and predict these multiple labels. But machine learning models are very good at taking multiple labels without noise and building a model to predict the observed data itself. So they basically took this machine learning process and flipped it on its head and said, we're not going to predict labels from data. We're going to predict data from labels. And what you get then is essentially a generative process where, given some stellar labels, you can predict what you think the spectra will look like. In this case, the true spectra here are in black, and the model spectra predicted by this machine learning model are in this teal here. And you can see it's quite close. And the teal, it's hard to see here, but they actually have uncertainties on the predicted models. And what that means is now you have a data-driven generative model based on machine learning that allows you, given your parameters in question, allow you to predict the data that you'll see. And if any of you have done any maximum likelihood inference or Bayesian inference, that sounds like something you can work with, right? You can do a gradient descent, or you can do an MCMC on that, and you can fit, given some data, you can figure out what those parameters are. And this was very cool because what they ended up doing was they could show that using this model far outperformed any naive machine learning model where you're trying to predict labels from data, and also outperformed any physics-based model where you're trying to essentially simulate the physical processes in the star to predict what the spectra are doing. And particularly, it outperformed those models when you went to the very high noise data, where you don't have very, very good constraints on the spectra. So I think this is a really cool way to say, like, we're going to take a machine learning model that doesn't really work out of the box, and we're going to look at it in a new way in order to apply it to the types of data that we see in astronomy. So we can make progress, I think, in machine learning by thinking outside of the box in this way and adapting these methods from other fields to the specific circumstances of astronomy. So those are the three case studies that I had that I wanted to talk through. Generalizing the Lomscargel periodogram, where we basically take a statistical method, break it open, extend it, do something different, and apply it to our data. Image-specific databases, where we haven't come up with the solution yet, but we're on our way there by defining clearly what the weaknesses are with the current set of systems that are out there. And also this kind of new look at machine learning, predicting data from labels rather than predicting labels from data in order to do inference and do a very nice study of these parameters. So that's the conclusion right there. I think I made the point in the beginning that statistics, data mining, and machine learning don't work in astronomy, and they don't work if you just try to apply things out of the box for the most part. But if you start to look at things in a different light, then we can make progress. So here's my contact info right here, and you can feel free to get in touch with me. And if I think we have time for a few questions right now.
In the last thing you showed, where you reverted the model, do you decompose the spectra into, let's say, different material spectra, or does the model by itself learn, for example, the single material emission lines?
Yeah, in this case, for the Canon paper, it was the original paper. They basically just used the simplest model possible. They used a linear regression, and they said that this is, you could go further and start looking at more complicated models to see what happens. But even just for the simple linear regression, where you're predicting point by point without any knowledge of correlations between neighboring bins in the spectra, they were able to get pretty good results. So I think that paper, that was a couple of years ago, but they treated that as kind of the initial study to say, like, this is something that should be explored more. And even the initial simplest approach was pretty good.
Not a question, but a comment. It seems your conclusion that these things, they don't work unless you change them, and then they do work, seems to me a little bit facetious, because it seems that if you try to just use these things out of the box, you're not even doing your due diligence. So it seems to me that what you just described is that they do work if you do them separately.
Yeah, I was being a bit facetious. I think they do work, but the point that I like to make often, because I come across this with students a lot, is that students discover some machine learning method that seems exciting that's worked somewhere else, and they hope that they can just plug and chug their data and not think about it. But you really do need to, like you said, do your due diligence and think about what the method is doing.
I would have a question about your first example with the periodicity. And you mentioned if you just fit to the individual bands, you don't get a good result. But if you use this combined model, you get a much better result. But it seems to me this is not really a question about statistics, but more like a question about, the question you are asking to the data, right? Because it just depends on how you combine the different filters and, whether you have an assumption that they should contain a common periodicity or not.
Yeah, absolutely. It gets a little bit complicated because I focused on one view of the Lumskargel periodogram here, which is its connection to least squared model fitting. There's another view of Lumskargel, which is basically that it's derived from the fast Fourier transform applied to unequally spaced data. And so I think in the past, most people have viewed it from that perspective. Like the periodogram is something you compute on data, and you get this thing that's like a Fourier periodogram, and you don't question the underlying assumptions because it's effectively Fourier analysis. But if you look at it from this other view and kind of tweak the model underneath, then so maybe it's not about statistics, maybe it's about modeling, but it is kind of this statistical method that you have to do your due diligence and think about what's going on under the hood to use it well.
Yeah,
I would like to come back on the second use case about databases, and I was surprised not to see mention, or maybe it was in the you know, support paper, let's say, mentioning the QServe database that is being, I mean, the setup which is being developed for LSST, which presumably would, at least I think we should try to support that kind of use case, obviously.
Yeah, yeah. So we didn't explore QServe, I think, because it was not mature enough at the time that we started the project. But again, this is something to look at because it's being developed specifically for that. Interestingly, SciDB was, if you look at 3-4 years ago, SciDB was the project being developed for LSST, and for various reasons, it's turned out not to be the best option going forward. All right, thanks very much.